Peering deep into the universe, astronomers probe the clash of cosmic forces. The obliteration of matter and energy. We glimpse the limits of time and space in the strange death of a star. There is no vision more reassuring. The endless cycles of the sun and the moon. The heavens ceaselessly turning. The night sky appears eternal and unchanging. Modern astronomy has given us a much different vision of a universe that roils and vents its rage. That vision comes together in the death throes of a giant star. Its surface is a stormy sea of fire. As superheated gas rises and sinks. Giant waves form. Solar tsunamis 1,000 kilometers high. Immense loops of hot electrified gas, larger than the Earth, blast into its atmosphere. Deep within its core, the star has begun to collapse in on itself. That causes the star to erupt in a violent supernova. In its wake, the explosion leaves a trail of colorful filaments and luminous, billowing clouds. Remarkably, the death of one star gives rise to a whole new generation of others. This cycle of death and birth has defined the history of our Milky Way galaxy and that of billions of other galaxies in the universe beyond. Our own vision of space has been shaped by a handful of rare exploding stars bright enough to be seen by the naked eye. In the year 1054, stargazers in North America spotted a supernova near a crescent moon. The same event was recorded in China, Korea, and the Middle East. The astronomer Tycho Brahe saw one in 1572. He wrote, "I was led into such perplexity by the unbelievability of the thing that I began to doubt the faith of my own eyes." Johannes Kepler recorded the next one in 1604. Galileo used it to make his case for a whole new approach to astronomy, based on the idea that change is a fundamental part of the cosmos. To find out how stars shape our universe, astronomers are employing an arsenal of new technology. From giant telescopes perched on high mountains to a fleet of instruments in space. When we look through a telescope at the stars, we are seeing the visible light they emit. But this is just a small part of what is known as the electromagnetic spectrum. At one end of this spectrum are short, high-energy X-rays and gamma rays. At the other end, long, low-energy radio waves. Huge arrays of radio telescopes are now being used to collect low-energy radio signals emitted by stars far off in the universe. Scientists use them to look through nebulas and gas clouds, to see the objects inside. At the other end of the spectrum are ultraviolet, X-rays, and gamma rays. The short wavelength of X-rays allow doctors to send them through our bodies to look for bone fractures. Astronomers look for them in space as evidence of the most violent processes in our universe. What shapes the cosmos at large is visible close to home. Our Sun is a medium-sized star with a surface temperature of nearly 6,000 degrees Celsius. Deep within its core, the temperature rises to 15 million degrees Celsius. High heat and pressure initiate nuclear fusion reactions that convert hydrogen to helium, releasing energy. The Sun, like all other stars, spends its life fighting gravity. Energy pushing out from its core keeps its outer layers from collapsing in. The Sun produces enough energy to hold gravity in check for billions of years. Not so for a large star. It burns hot and fast, steadily packing its core with heavier and heavier elements. When its core reaches a critical threshold, it no longer produces enough energy to counter gravity. It collapses, then explodes. Destruction is by no means a supernova's only legacy. The explosion seeds its environment with carbon, oxygen, iron, and other elements necessary for life as we know it. Shock waves from the blast can trigger the birth of new stars. In fact, star hatcheries set in motion by supernovae percolate all around our galaxy. Among them is a great luminous cloud of gas and dust known as the Orion Nebula.